Alright, dear students. So, in this lesson, we will cover the important topics of Unit 4 Organic Chemistry and Food Chemistry. Um, so, again, I am only covering the important topics. You need to do all the past exams and cover do all the questions, yeah, from your past exam I've given you, and also go through the topics in the book. Try to hit every single type of question and all the topics, but here I'm covering the important ones. So first of all, you need to know that the organic molecule can be represented in four ways. So the first one is you can write molecular formula. Yeah, in molecular formulas you simply write the number of different types of atom. For example, if you have butane or butanol, you can write C4H9OH, or you can also write molecular formula for butanol as C4H10O. Both are acceptable. And then there is structural formula, very commonly asked in the exam to write structural formula of something, and because of the simple mistakes, student lose marks. So to write a structural formula, you need to show every single bond. Emphasis is on every. You want to show every single bond. Yeah. For example, if you have 4 carbons, you need to connect 4 carbons with a single bond. And then, of course, each carbon can have, let's say, terminal carbons can have 3 hydrogens. And because here they have not mentioned is butane 1 ol or 2 ol, so it doesn't matter for at this stage. I'm just giving you example. Hydrogen. All right. Let's say if I write OH like this and it is 1 mark question, you'll get 0 marks. Why? Because I've not shown the single bond between oxygen and hydrogen. So I need to remove this and then write a single bond and then hydrogen. Now it is correct structural formula of butane 1 ol. Now semi-structural formula is what? Sometimes it is also called condensed formula. Semi-structural formula is when you condense. For example, there is 1 carbon and 3 hydrogen, so I just write them as CH3. All right. Still there is 3 so you were not showing any single bond. If there's a double bond, yes, we need to show, but if there's single bond, you don't need to. Now then we have C and 2 hydrogens attached, so I write CH2, and then another CH2, so I'll write CH2, and then another CH2, I'll write CH2, and then there is OH. You can write OH before the CH2. And then there is a skeletal formula. Many students think that this is not important, but trust me, there are questions where they ask you to write a skeletal formula, or they give you skeletal formulas and they expect you to know everything. So in this case, each corner is 1 carbon, and hydrogens we don't show. Other than hydrogen, if you have OH, Cl, double bond, you need to show. So we start with carbon and then zigzag 2, 3. So this is carbon 1 with 3 hydrogen, carbon 2 with 2 hydrogen, carbon 3, carbon 4. So 1, 2, 3, 4. Now with carbon 4, OH is attached, you need to show that OH. So this way of writing is called skeletal formula. You need to know all these 4 types, and when question asks you, you should be able to answer accordingly. Like what they're asking you. Are they asking you to write structure formula, semi-structure formula, skeletal formula? If they don't mention any of these, I recommend that you write semi-structure formula. It saves time and space. All right. Let's say if you have to write methane, let's say 5-methyl it's not possible, 2-methyl butanol. Yeah. So, and they ask you to write a structural formula. So first of all, it's butanol, so you need to draw 4 carbons. It is 2-methyl, you need to draw another carbon here and make a meth. So even branches, you need to show all the bonds. All right. Now, all the single bonds are shown. That is 2-methyl butanol. Structure formula. All right. Now, if you need to show the semi-structure formula for this one, you'll write CH3, the first one. All right, that is done. And now then you write second carbon, CH, that is done. And after second carbon, you need to show the branch, and branch must be in the bracket CH3, and then continue with CH2, and then CH3. All right. So this is semi-structural formula. Okay, next one is function group. You need to know all the function groups, like most commonly used in your textbook study design, but you need to be able to name only the one which I've ticked off. For example, carboxylic acid, alcohols, primary amines, alkenes, alkynes, haloalkane. All right. Of course, alkanes, amide, ester. But for aldehyde and for ketone, you don't need to know the names, how to name them, but you should be able to recognize if it is given in the exam. All right. So you can't say that it was not in the study design, so I don't know which one is aldehyde and ketone. No. You should be able to recognize the function group even if it is not there in the study design for naming. So, with the carbonyl, if you have carbonyl group and you attach one side OH and other side is any hydrogen, for example, or carbon containing group, that is carboxylic acid. Yeah, that is carboxylic acid. If instead of OH you have OR, now it becomes ester. All right. If instead of OR you have NH2 attached, now it becomes amide. All right. So functional group has its derivatives. It could be carboxylic acid, ester, or amide. Similarly, if you have carbon oxygen double bond, and both sides you have carbon containing group like CH3 or C2H5, so this type of group is called ketone. So you don't need to name these groups, but you should be able to know that this is ketone group and that ends with ONE, like propanone, because you have not done naming of other things. So if you see anything ending with ONE, that is a ketone, because ketone also has ONE at the end. And aldehyde has one side hydrogen, other side could be hydrogen or could be any carbon containing group, but one side it must have hydrogen. On the other side, it may or may not have hydrogen. All right, but one side is must. So that is aldehyde, and it ends with the name Al. Sounds like methanol, but it's methanol or ethanol with Al. Remember that because aldehyde starts with Al, the name ends with also Al. All right. So these are the function group you need to know, because in the exam they might ask you to encircle the group. Now, naming organic molecules, I can't, of course, go into the details of every single organic class and explaining, but I'll quickly do a few examples for you. Alkanes, let's say if you're asked to write the name for 2,3 dimethyl pentane. All right. So first of all, you know that there are 5 carbons. So you draw 5 carbons. I'm writing in structure formulas. 1, 2, 3, 4, 5. Now, second, it says that on the second and third carbon you have dimethyl group. So I'll draw CH3 and second and third, I'll keep hydrogen here. All right. and then rest just put hydrogen everywhere. That becomes 2,3-dimethyl and pentane. Why it is called pentane? Because there are only single bonds. When there are only carbon-carbon single bonds present, it's alkane. So whenever you have a name given to you, start with the parent carbon. So there are 5 carbons and then follow whatever it says. Remember that when you're naming some organic molecule, you need to separate the number by a comma. Alright. So 2, 3, or you can say 3, 3. So, and when you separate a number and an alphabet, always use this hyphen. Now let's do some questions. If you have CH3, CH and double bond CH, and then CH2, CH, CH3, let's say, alright, and CH3. Now start numbering from the side where the double bond is closer, not where the branch is closer. Remember that. That rule of branch closer is followed only for alkane or when there is no function group. If there is a function group present, you must start the numbering from the side where that function group is closer. Here we said that 1, 2, 3 because these are the branches and there is no function group. But here function group is double bond. So carbon number 1 is this, 2, 3, 4, 5, 6. So first we have to name the branch. So I'll say 5-methyl because carbon number 5 has the methyl group, and then because there are 6 carbon hex and carbon number 2 has the double bond, the smaller carbon always gets 2-ene. Alright, same naming is for alkynes. Let's see for alcohols, CH3, CH2, CH3, let's say, and you have OH here. We start numbering from this side again because the functional group is closer. So 1, 2, 3, 4, I'll say butane, 2 all. Alright. They may accept 2-butanol, but it's not recommended. You write this way. Now carboxylic acid, for example, if you have CH3, CH, CH2, COOH, always carbon number 1 is the one which is carbonyl group. So carbon number 1, 2, 3, 4. So because we have to name the branches always first. So carbon number 3 has methyl group. I'll say 3-methyl. And including carbonyl carbon, how many carbons in total? 4. Butanoic acid. Butanoic acid. Alright. And then ester. Ester has one side oxygen and carbon containing group. Oxygen is there. Alright. On the other side, it could have only hydrogen or carbon. So we have to name the thing which is with oxygen first, and then the thing with, and then remaining part next. Alright. So this is, so the one in the black circle is always named as YL, and remaining carbon always with OATE. Alright, so this would be because there is one carbon, so that is methyl. Alright, so this part is done, and after this the total carbons remaining are 2, so 2 is ethanoate. Alright, again this is quick revision for your naming. You need to do a lot of practice. Now after that, they often ask you to differentiate between different classes of organic compound, and how can you do that? Imagine that if you have 2 test tubes and one test tube has alcohol in it, alright, alcohol in it, let's say CH3, and other has some alkane, and both are colorless. Some alkane, both are colorless. What simple test can you do to distinguish between these two? Yeah, so you add few drops of acid, carboxylic acid in both. Alcohol reacts with carboxylic acid to form ester. So you add few drops of carboxylic acid in both. The one which forms ester smell good like perfume. You add few drops of carboxylic acid in both and smell. The one which good smell after adding the drops is alcohol, and other one then must be alkane. All right. So add carboxylic acid in both test tube. The alcohol react with carboxylic acid to produce ester. Ester smell good, like different fruits, and you will tell that, oh, this one is ester. It means alcohol is present in it. So this is a simple test. If they ask you to write the equation, you can write equation for esterification. For example, if methanol was present, you add, let's say, methanoic acid. All right, sorry, ethanoic acid, OH, and then it becomes CH3O, CH3. So it becomes methyl ethanoate. So that ester is formed. Now, if you're given, let's say, two test tubes, one contains primary alcohol and one contains secondary or tertiary alcohol, and they ask you to differentiate between the two. In one you have primary or secondary alcohols, and in one you have tertiary alcohols, and they ask you to differentiate which one has tertiary, which one has primary. You add oxidizing agent. All right, for example, Cr2O72 minus or MnO4 in both test tube. Tertiary alcohols, they don't react with the oxidizing agent, they don't oxidize further, but primary and secondary they do. So if the color of this changes, it is primary or secondary alcohol. If color remains same, that is a tertiary alcohol. So it means that this is not undergoing reduction. It is oxidizing agent, so it should undergo reduction if it reacts. All right. And the color change is happening because the chromium oxidation state is changing. Now alcohols, if they give you two test tube, all right, one contains alcohol and other contains acid, all right, carboxylic acid, methanoic acid, propanoic acid, alcohol, both are colorless. What you can do, the simple test is to put the litmus paper in both. The one which turns red is acid, because acid will change the litmus color paper. Another way is to add little bit of base like sodium carbonate. It will react with acid, and on the other hand, alcohol is neutral, it will not react. So if sodium carbonate reacts with acid, it will produce CO2. So if you see bubbles in one of the test tube, that is acid. So a carboxylic acid can be differentiated by either litmus paper or alcohol. Very common question. Alkane and alkene. All right. If you have two test tubes and one is alkane and one is alkene, so all right, let's say this is alkane ANE and this test tube contains something alkene. You add few drops of Br2 in both. Now bromine Br2 has brown color. It reacts with alkene. Why? Because alkene is double bond and bromine goes and adds on top of the bromine, it becomes single bond, so it becomes colorless. So if it is alkene, the color of the bromine will disappear, the brown color. If it is alkane, alkane is already saturated, you add bromine, bromine will just remain there as a brown color. So you add bromine, decolorization or the color disappear means alkene is present. If color remains, it is alkane. And then, of course, the favorite part for many students is organic reactions pathways. If you have alkene present, all right, most common one, remember that alkene has a double bond, minimum one double bond. If you add something like HCl or H2O, whatever you're adding, break into two parts. So one part you add on one carbon, doubly bonded carbon, and second part you add on the second carbon, and make this a single bond. That's it. So if you have ethene starting point, see here, you're adding HCl. So H goes on top of one carbon, chlorine goes one carbon, and it becomes this. Where is that? So this was one of the double bonded carbon. So you added hydrogen, it becomes this. And on the second carbon, you added chlorine, it becomes. So addition of HCl, HBr will give you haloalkane, like chloroalkane. All right. And this haloalkane, which is you getting from the reaction of alkene with HCl or HBr, you can also obtain from alkane, but a different reaction, not HCl, but chlorine under UV light. You need to write both of these things when you do this reaction. If you don't write UV light, you may not get full marks. All right. Now this haloalkane, chloroalkane, bromoalkanes are very important starting point for many reactions. So if you know that how to prepare haloalkane, you can do many reactions. Again, haloalkane can be prepared from alkene. If you want to prepare bromoethane, add HBr. If you want to prepare chloroalkane, add HCl. All right, this is one pathway. Second is that you start with ethane and add chlorine gas with UV light. Depends what the question says. If question asks you to start with alkane, you start from here. If this question asks you to start from alkene, start from here. Now once you have haloalkane, you react with sodium hydroxide. The OH will replace chlorine and you get alcohol. All right. Now we have seen in the previous page, using alcohol react with you can oxidize it. It becomes acid. All right. And you can also, alcohol can be oxidized, and remember that oxidizing agent you need to write both things, Cr2O7 2- / H positive. If you write just this, you may not get full marks. You need to write both, and preferably with the state as well, AQ, but not important. But important thing is that you write the oxidizing agent and also write the H positive. All right. And once you have acid can react with alcohol. ROH mean any alcohol, methanol, ethanol, in the acidic medium and give you ester. All right. Alkene can directly give you alcohol if you react with water in the presence of H3PO4. This is direct method. All right. I'll give you another pathway. You need to know these pathways really well. All right. Again, we start with propene, which is an alkene. If you add HCl on propene, it becomes this 1-chloropropane. All right. Now 1-chloropropane, the chlorine is easily replaced with OH if you react with sodium hydroxide. All right. Once you have alcohol using this oxidizing agent can become ketone first, but if you use for exam and you use this condition, you can directly make acid. Like you can directly go to acid. It's okay. All right. So you have this in front of you. So this chlorine you can change using KOH or sodium hydroxide to make alcohol, or you can use ammonia here to replace Cl with NH2. So you can, from this single haloalkane, which you can get from alkene or from alkane, this one alkane, you can make alcohol if you add sodium hydroxide or KOH. You can make amine if you add ammonia. All right, it can go in both ways. So practice. Almost every year we have this flow chart where you have to fill in these boxes. Yeah, this is same thing again. The oxidizing agent, either you can write in charged form, or like for example, if you write Cr2O7 2 minus, or to remove these 2 minus you can also add K2. So important is this: Cr2O7 2 minus in the ionic form with H positive, or if you write K2 Cr2O7, you don't write any charge because minus 2 is balanced by 2 Ks. Alright, N slash H positive. Both are okay. Alright, you write this or this, both are acceptable, but make sure your charge is right. Now, physical properties of organic molecule, mistake here, molecule. Physical properties of organic molecule means the density, melting point, boiling point, solubility, all these things. And remember that when they ask you a question about the physical properties of organic molecule, you need to mention, when you're reasoning those questions, one of these forces, intermolecular forces, either hydrogen bond, dipole bond, or dispersion forces. One of the three forces you need to mention to justify your answer. All right. For example, if they ask you if you have, please read these dot points. If they ask you if you have CH3 and OH, or alcohol, and you have C double bond O, OH and H, both have one carbon, and one is acid, one is methanol. Which one is more soluble in water? Which one is higher boiling point, melting point? Think about the forces. The methanol can make hydrogen bond because of this group, and carboxylic acid can also do that. Minus, plus, both can make hydrogen bond. But carboxylic acid can make additional dipole bond because of this positive and negative bond. So because of the additional dipole bond present, it will be it is more polar. So remember that something which is more polar will dissolve better in water. Water is polar molecule. The ionic compound NaCl, why they dissolve immediately? Because they are not all the ionic compound dissolve that quick, but ionic compound, they are like fully polar, so they dissolve in water, those which dissolve. Similarly, if both are polar, the one which is more polar will dissolve faster in water. So the reason should include that because the carboxylic acid, they have hydrogen bond as well as dipole bond, so it dissolves better. Similarly, if you have CH3, CH2, CH2 and OH versus CH3OH, which one dissolves better? Both are forming hydrogen bond with water, but the propanol has hydrophobic part bigger, so it will be, that part will decrease the solubility of propanol. All right, so this dissolves still better than this. Read all these dot points and make sure your dot points, when you give the reasons for physical properties, you include at least one of the intermolecular forces, like either dispersion forces, dipole bond, yeah, and viscosity and flash point. All this is reading material. Please read this. Now, the second part of area of study 1 of unit 4 is instrumental analysis and chromatography. I'll start with chromatography. Paper or thin layer chromatography, similar principle. I'm not going to much detail. RF factor is most commonly asked in the thin layer chromatography or paper chromatography. What is that? It is the distance covered by the compound. For example, if you have R here, So R was initially here. So the distance this much, let's say 5.5 centimeter, divided by the from this point the total solvent distance, yeah, covered by that. Let's say it is 18. So whatever answer come is the RF. Important thing is that many students make, which I did just now, that this 18 is the distance traveled from here, and we want to know the distance from the origin, which is here. So it's not 18, it is 16, because we have to minus these 2 centimeter. The distance is from the origin, not from the starting point. Origin mean where the spot is present, where the spot was placed. Similarly, the distance covered by R is not 5.5, it is 3.5. Why? Because we have to minus the, it's very important. So remember that thing, the distance you have to calculate from the origin of the compound, not from the origin of the TLC. Alright, so if they've given you scale like that, it may easily deceive you, so make sure that. And then how would you remember that? It is the distance covered by compound over distance covered by solvent, or solvent over compound. Remember that RF value is always less than 1. So if it is less than 1, it means that compound, the smaller number is always on top, and solvent, the bigger number, is always at the bottom. So the answer is less than 1. Now here they ask you the RF value of the dye most strongly adsorbed onto the stationary. Now remember that the stationary phase in TLC is polar. The back of the slide, the material which is sticking on the back of the slide is called stationary phase because it's not moving. That is polar. And when you place in the beaker, the solvent which moves up, taking the compounds with it, is called mobile phase, is non-polar. So like dissolve like. So if there is a polar compound moving here, and the stationary phase is also polar, the stationary phase will hold it with it, because they love each other. Polar loves polar. So it means that the polar compound will be like here, and non-polar compound will be there. So non-polar compounds will travel faster, all right, and non-polar compound will travel slowly, because the polar stationary phase is holding them because of the attraction. Now HPLC is different from the normal chromatography. H mean high, P mean performance or pressure. So because this column is different, this is so tightly packed and it is horizontal, we need a pump here, all right, to push the solvent. While in the liquid chromatography, or in liquid chromatography, the solvent comes using the gravitational force, yeah. But here the column is horizontal mostly. Even if not horizontal, it's so tightly packed that solvent needs a pump to push the solvent through it. So it is high pressure liquid chromatography or high performance. Now there are two types of HPLC, the normal phase and reverse phase. In normal phase, the stationary phase inside is polar, just like TLC, and the solvent which passes through is non-polar, all right. But this is not the common type of HPLC. Commonly the HPLC is reverse phase, all right. Reverse phase mean inside here the stationary phase is non-polar, all right. Non-polar, they make it non-polar by attaching long carbon chain of C18 or something, and the solvent which passes through is polar. The mobile phase is polar, all right. Again, the inside column which is tightly packed is non-polar. Now it means that if your sample is non-polar, it will love non-polar and come out late. In reverse phase HPLC, because the stationary phase is non-polar, it will hold the non-polar back and let polar go. All right. And if let's say two compounds have similar polarity, so one which is larger in size will stick back. Why? Because non-polar loves non-polar, and the larger molecule, if they have larger carbon chains, let's say, they will have more dispersion forces. So basically, the compounds which will come slow in the column is either non-polar. All right. If two things are exactly they're both non-polar, then the one which is larger in size which will come slow. All right. Now see how uh, if the column is tightly packed, the resolution is better. Resolution mean the two compounds you can collect them easily. They are separated now. Here they are not separated. At this point you will collect partly A and partly B. All right. So why? Because this column size is like 5 microns, slightly bigger, and this is 1 micron, smaller size. So columns are really important in HPLC. Now retention time. The time which it takes for a molecule to come out from the HPLC column is called retention time. Like retention mean for how long the column can retain the material. All right. Let's say this is time in a minute. This molecule comes out after 32 minutes, or let's say at just in the middle from here. The time is given here 30.63 minutes. 30 minutes, yeah. And this one is coming out at something like 12 point something, yeah. So the time from the start to this time is called retention time. For how long it is, at this point you will see that you can collect it from the machine. It's coming out now. Now you see here, because it is reverse phase chromatography, the ethanol which is smallest and the most polar is wait a second, is it reverse phase or normal phase? Okay, all they are polar, but in this case now, are they using, let me see,